and travels at the light speed. And that's the understanding that we have today.
So energy carried by the electromagnetic wave. That's the amount of energy. So energy is going to be carried by the magnetic field component as well as the electric field component. All right, the lowercase u in this case represents the energy density. That's the amount of energy stored within the volume of the electric as well as the magnetic fields. So 1/2 of that energy is going to be carried by the electric field component and the other half by the magnetic field component. So the energy density of the electric field component will be identical to the energy density of the magnetic field component. Like terms cancel. Then let's express the strength of the electric field in terms of the strength of the magnetic field. And I want you to notice that the term in front of the magnetic field component is the same as the speed of light. So the strength of the electric field is going to be speed of light times larger than the strength of the magnetic field. So it's going to be 300 million times larger than the strength of the magnetic field. So,
and the amount of energy that the light carries per second is known as power. And the amount of energy that the light carries per second passing a region, some kind of a surface, is known as intensity. So the amount of energy carried by light per second intercepted by an area per area is known as intensity. Amount of energy carried by light per second or transferred by light per second intercepted by an area is known as intensity. So if there is a region, some kind of a surface that can intercept that area per second, that's the amount of intensity which is going to be located at that area. So this is known as the electromagnetic wave intensity. Is related to the amount of energy which is transferred, which is carried by light per time per unit area. I just hate those kind of definitions. The reason is because it's mouthful. Okay, so we got the electromagnetic wave coming this way. Because it's a wave, it carries energy. So the amount of energy that it's going to carry per second per time intercepted by this area, small area that we're looking at, is known as the intensity of light.
now let's come up with a mathematical expression for intensity. Intensity is the amount of power intercepted. Power is the amount of energy per second, per time. So now we come up with our intensity equation. So here, capital U is the energy. It needs to be expressed in terms of the energy density, but that's the amount of energy stored within the volume of the electromagnetic wave. So we're going to take a look at a small volume of a region that carries energy. All right, so we got the electromagnetic wave coming in at the light speed. And this is the distance that it's going to travel within that time period. So that becomes the base of that volume. And this is the area of the volume, which is going to store the energy. And now volume expression is the base, which is the light moving at the light speed within that certain time period, and the area that we're looking at. So we're expressing the total energy in terms of the energy density. So the total energy divided by the time and the area is going to give us the intensity. So the like terms cancel out. As a result, we come up with an expression that says the energy density traveling at the light speed is going to give us the intensity of that electromagnetic wave. So the intensity could be expressed in terms of the intensity of the electric field component or the intensity of the magnetic field component. So it's going to give us the total intensity. Let's get back to the question. of a tail of a comet pointing away from the sun? Is it possible that the electromagnetic waves can transfer momentum? Let's find out.
All right, so
here at the Air Force Research Laboratory in the sunny Mojave Desert, they're working on solar propulsion. The pressure of sunlight on solar panels could push ships through space, or the light could be converted into power for electric motors. Or an inflatable solar concentrator like this could heat the propellant in rocket engines. This would allow for rocketry, but with much lighter fuel and much more efficiency.
all right, so if we're talking about solar sails, which means that the electromagnetic waves must be creating some kind of pressure. This is known as the radiation pressure. Pressure implies force acting on an area. Force implies transfer of momentum. So, which means that the electromagnetic waves, contrary to what Newton thought, can transfer momentum. Newton didn't think that the waves could transfer momentum. That's the reason why he was favoring the concept of light being a particle. Contrary to what he thought, waves can also transfer momentum. They got intensity, they transfer energy, they create radiation pressure. Pressure implies that there's force acting on that surface, and force implies that change in momentum. Force is how fast the momentum changes. And when there's force, it causes change in momentum within that direction. So energy gets transferred, momentum gets transferred. So waves in general, contrary to what Newton thought, can and will transfer momentum.
All right, so let's talk about the radiation pressure. As it so happens that the energy can transfer momentum, as Maxwell found out. P represents the momentum in this case, so energy is going to be used. So that's the stored energy inside the magnetic field. And the external force is what changes momentum. And same force acting on an area is going to cause a pressure, otherwise known as the radiation pressure. So that's your radiation pressure term. And the radiation pressure could be expressed in terms of the highlighted terms. Highlighted terms represent the intensity. So the intensity of light divided by the light speed is going to give us the radiation pressure. So that's the amount of force that the light is going to exert on a given surface area. S represents the total intensity. So it's going to be a combination of the intensity of the incident electromagnetic wave and the reflected electromagnetic wave. So that's the
Space was considered a vacuum, except for a curious clue, the tail of a comet. Regardless of the direction it traveled, its tail always pointed away from the sun.
All right, so what's pushing the tail of a comet? Tail of a comet away from the sun. We know today that those are particles ejected by the sun, but let's just ignore that. Light coming out of the sun, electromagnetic waves in general, can apply and exert a radiation pressure, meaning that they can transfer momentum to these particles, thereby pushing these particles away from the sun. And that's the reason why the tail of a comet is always going to point away from the sun. So what is the nature of light so far? Well, obviously, Huygens was right in all appearance, and Newton was wrong in all appearance. It looks like light is a wave. A famous experiment in 1801 or 1803, depending upon what your source is, conducted by Thomas Young, settled that debate.
Here's just one of the reasons Young is so clever. He decides to shed a little light on light in 1803. Okay, watch this bit of magic. Here we have a candle, a lens, a card with a pinhole in it, and one with 2 slits. Okay, shine the light from the candle through the lens so you get a nice focused beam. Then carefully place your cards so that the light goes first through the pinhole, then the slits, and voila! Young realizes the light going through the slits and mingling must be coming in light waves, because this interference pattern could only be made by waves. Question is, what do light waves travel in? They decide to call the mystery stuff ether, and the hunt for it shakes up the brains of most of the 19th century's complement of serious propeller heads. Now, the biggest propeller in Germany at the time is a Harumph type, name of Helmholtz, prof at the University of Berlin, and he puts one of his whiz kids, Hertz, onto the case. Here is a very oversimple view, of what Hertz does. Say this water is that mystery ether stuff, right? Hertz is into electricity at the time and wonders if it travels through ether in waves like light. And he finds out it does. An electric spark sends out electric waves moving like light waves, or waves in the sea.
Discovers. On the screen, he ends up getting a fringe pattern. You got dark fringes and you got bright fringes, so the question is, what's causing the fringe pattern? This is otherwise known as a double-slit experiment. So you got a single light source, and there are 2 double slits. You got double slits, the light is going to go through both slits, and then it's going to give you a fringe pattern. What's responsible for the dark fringes? That's the absence of light. What's responsible for bright fringes, which means the presence of light? And towards the middle of it, the light is going to become brighter. So the dark fringes are obviously caused by an interference pattern, so that's a destructive interference. The bright fringes must have been caused by constructive interference. All right, when the interference is constructive, it's going to give you a bright fringe. Once again, here's another bright fringe. If it's a destructive interference, it's going to give you dark fringe. Only the waves can give you interference patterns. It's going to give you bright fringes. If light is composed of waves, that explains why we get bright as well as the dark fringes. So the interference of light, the waves, etc. So everything starts up with Huygens in 1670. He comes up with the wave theory of light in 1670s. And he comes up with this theory based upon the superposition of waves leading to constructive as well as the destructive interference patterns.